Welcome to session 8 on societal issues. The first talk is going to be on, sorry, I need my glasses, on dynamics, macroscopic quantum phenomena, motion of topological defects, genesis and progression of cancer, and framework for non-equilibrium processes. This is definitely one talk, right?
But yeah. Right. I then stop it. Yeah, stop it. Then I can play. Yeah, just stay there. It will be connected. Then I started playing. Yeah. Okay. First, I'm very happy to be back here, and also I thank the committee very much to give me the opportunity to present some of our results. They asked me to give some kind of a forward-looking reports. So I think. In the following 20 minutes or so, I will give you two pieces of forward-looking things. I hope at least you will like one of them. Oh. So it's the first piece.
Happy birthday to you. Happy birthday to you. Happy birthday to you. Happy birthday to you. Happy birthday to you.
So basically, Tony is, as you can see, in China, has been liked by both politicians and ordinary people, and also liked by the professors as well as high school, middle school students.
Professor Leggett, here is a present for you. This Chinese calligraphy was from my father's colleague's grandfather. He is 93 years old now, and he wished you a good health. Happy birthday, Professor Leggett.
Happy birthday, Professor Leggett.
Hello, Tony. Happy birthday. 生日快乐.
I couldn't understand the word of it, but I hope you and Haruka can understand it. So, okay, so part here. Okay. So it's my first piece of a forward looking, and so what really show, maybe my friends come to help me, give for the forward looking and what in here. That's a Chinese calligraph. Means good health and longevity. And it's by an artist who, as you just heard, is 94 years old. So you see, there's a long way to go. Maybe 90 years later, Tony's 90 years birthday, we will get another one from over 100 years artist. Yeah.
Thank you.
Yeah.
Thank you very much.
Okay. Yes, Tony. Yeah. Oh, by the way, this video was produced by my friend, as a physicist turned entrepreneur, Tony, get to know in Shanghai. Yes, he came all the way to bring us the gift here. Yeah. Okay. My next piece also kind of forward-looking. It's probably some of our colleagues may how to, which one here? Okay. Nope. Oh, okay. Yeah, it's actually the story. It's one piece of a story. I started when I worked with Tony as work for my PhD. So it's a story I called metric trajectory to a current stop. I think we found a way to formulate the non-equilibrium process in a consistent way. We call this foundation of statistical mechanics and thermodynamics through various intermediate stages. Okay, so then just start from here. In the mid-80s, when I started working with Tony, he suggested me to look into the two-level system. Okay, and I spent some time, learned the techniques, and I feel I was ready to do something. Then I discussed with fellow students like Matthew and Alan, and also a postdoc, William. And then I got the impression they practically solve all the important parts of a problem related to two-level system. So I was a little bit frustrated. Then came with Tony another new postdoc, Yuan Raman. Then he suggested maybe we can try the technique to a dynamic one. It's a driven two-level system, which can be known as Landau-Zener transition. So basically, he suggested that we maybe look at that when coupled to a dissipative bus, maybe we'll get something interesting. And then after some time, you can see, indeed, we find out that when coupled to a dissipative bus, the behavior becomes extremely rich. I mean, without coupling to a bus, like here, it's symmetric. You will start from here, and you find out the probability number here will be the same. You start here and end up here. But when you put in the coupling to the bus, this up and down become asymmetric. And also, other factors come into play. Temperature, coupling strength, and so on. So it's a pretty rich thing. Then this is a part of my PhD thesis. I got the degree. Then move on to work with David Sollers. And David said, well, he told me, he said that you are kind of familiar with dynamics. And he said, I have a problem in my mind, worrying me for about more than 20 years. Maybe there's some way we can do together to figure out what's really going on. So that's the vortex dynamics. The very essential issue is on the transverse force. So with David and also a few other collaborators, we've figured out how to compute the transverse force reliably from a microscopic theory. But all the calculation is basically based on symmetry and the topology, like the microscopic details. But David thought that he solved this. So he left the detail to me and asked me to fill in the details about, for example, how to compute the friction of a moving vortex and so on. And then that took me few more years then to finish this project, starting from a microscopic theory here. For superconductor will be the BCS theory. More precisely is Bogoliubov-de Gennes equation. And then we computed the response function. Turn out the transverse response function is precisely related to Barry phase, and the longitudinal response function is precisely linked to the friction. So that's this, I think, the dynamics here is very much similar to a problem Jean yesterday mentioned about. It's actually very, very similar. The interesting point, I think, probably, and it's for David here already know, as turn out we come back to what I learned with Tony is about the influence functional, conductor, negative mode, and so on. Basically, the mode turn out can be mapped into that problem, almost exactly the same way. So basically, kind of come back to that again. After this, one more thing. So it's my collaborators then did a direct measurement on the transverse force in a superconductor in Sweden. And I mean, I have not follow up the literature, but to my knowledge, it's probably one of the very, very few direct measurement on the transverse force on the moving vortex. And also the setup they use is a mechanical resonator. I think I heard about the mechanical resonator here. That's in previous talks. Okay. Now, so in the study in this century, I move into biology and to study the dynamic process in biology. So one of the first cases we encounter is about the stability and the robustness of a genetic switch. That's well known in biology. And was actually one of the biological cases established by physicists, by Max Delbrück and his group. But the puzzle is that biologically, they found out that the genetic switch is stable against almost all kinds of perturbations. That's on the one hand. And then on the other hand, this is a process simple enough. One can have a real theory based on the scientific mechanics and the biochemistry. So one can write down a full microscopic model. But it turned out naive way of dealing with this, then could not explain this stability. And we struggled this for a couple of years. Then we figured out a way to do this. It's by find out a new structure in the stochastic process, which I will come back. And then this is turned out to be one of our best laboratory and the theoretical side. So we keep on working on that on various aspects of this problem. But this is a kind of just like a ICE model in scientific mechanics, a kind of case examples. Then we move on to the real thing, and here, and last night I kind of feel I was sympathetic to Matthew about it's what we feel 10 years ago. We proposed a theory, new theory, for how cancer started, how cancer progressed. 10 years ago, virtually every biologist, every molecular biologist thought I was totally crazy. It's just impossible. And the essence of our theory is that basically we don't believe the mainstream, this mutation theory for cancer, is correct. In fact, we predict there will be cases one will get cancer without a mutation. So, and that time, no cancer biology would believe us. But by now, data have been accumulated and it turned out to be the case. So that's one of our first qualitative prediction. Our second prediction is that that's also a contrast to the belief of cancer biology that time, is that the cancer is, in principle, reversible. So if you know the right kind of dynamics, there will be a way you can reverse it, turn back to the healthy state. Well, after more than 10 years working on the issue, and I think now I can safely say, I didn't want to say this 10 years ago, because they thought I was already crazy enough. But now we can say our theory, in some sense, is a many-body physics theory. So treating the complex disease is a kind of one of the phases in a condensed matter. I mean, this is a very, very much low-energy condensed matter. So after working on about 5 different tumors, published more than nearly now 20 papers, and we summarize our case here. So by now, I think it's, and this is a small group of biologists started to accept our reasoning. So on this level, I think it's a series in principle correct. I will not going on into very detail here. I just want to bring up another piece, and it's kind of a side prediction of our theory, which is a developmental process. So start from a given cell, then in a body, then this turn into the functional cell types. So it's a lineage analysis, a cell type analysis. The one I want to bring up here is for 2 purposes. One, we have a quantitative dynamic theory which can predict the stages. And then on each critical stages, we can predict what the system should look like. Then one can do a measurement actually measurement have been done to check them up. So turn out we can, basically for this case, for our blood cell development process, we can predict one major group of developmental process. So that's one side. It's working, not only for cancer, for diseases. Diseases also working for normal biological process. Second point I want to bring this up is that turn out within a year, last year, there has been a big project on human cell type atlas. I think the theory we proposed 10 years ago is one of the precise theories they are looking at. Unfortunately, I wrote to the advocates of this cell type atlas. I haven't got any response back yet. Okay, so this is we look at the dynamic process of normal and abnormal biological process. So I think for most of the physicists sitting here, they probably don't care about such a biological process. So one of the issues you may care about is there anything like we heard this morning, fundamental or quantitative can come out of this? Indeed, we found out that there's a new structure embedded in a stochastic process. And so, as I actually have been discussing with Tony now before this paper, we'll discuss about this, and so I can tell you the first reaction for Tony is that, well, it is a magic, right? It's more or less your word. And then your second comment then to me, as far as I remember, you cannot be completely wrong, right? Okay, so this is what my discussion with Tony. Then actually during the development process of this theoretic framework, I did encounter some problem. And then I talked to David Stowers. And first, he asked me, "Are you sure you're right?" I said, "Yeah, I think I feel I'm right on this." Then he asked me to explain to what's the difficult issues I encountered. And then I explained to him. He said, "Let me think about this." Then 1 week later, he came up with a solution. The problem actually already kind of took me more than a year I could not solve. So it's And so result, we end up publish a paper together with the 3 authors. So it's David Saurus, and me, and one of his former students. So it's, there's some issues here, and I will show you the reasoning. And but our results have been summarized in this recent review here. So the story that the main point I want to show today is this structure can be served as the dynamic foundation for statistical mechanics and thermodynamics. So that means after more than 100 years of search, we may finally get the answer. What is a critical question? So the critical question actually is rather simple. I mean, everybody learn this in a college as a differential equation. You just write down a differential equation, say in n dimension, dx dt equal to fx, and x as n dimension, f will be any smooth function. So the question is, such a dynamic process allow the existence of energy-like function or Lyapunov function. So that has been the question. That's the first question. Second question is that if such a function exists, can we have a way to find this out? I mean, this is how any working scientist needs to know. You need, at the end of the day, we need a number. And, and then there's the issue of stochasticity and a noise concerning this. So Yahweh's will post a problem which every college student can understand. So getting this. It turns out it's one of the very hard problem. As far as I know, until some textbook in mathematics, a very recent one, the author still express the view probably no energy-like function could generally exist. So this basically, the textbook is like to phrase as a gradient system, means the existence of an energy-like function, or more general vector field dynamics. The difficulties can show up in following 4 aspects. One is dissipative. Another one is non-detailed binaries. Non-detailed binaries have a kind of a magnetic field-like structure, and it's non-linear. Sounds stable. And the noise, as we heard this morning, is typically multiplicative noise. So the scientific part of my presentation will be next 2 pages. This can be done. So let me come back to this equation. It's dx dt equal to fx plus a noise. Well, it's not exactly the Langevin equation in physics. As I said, this f is a dissipative and without a detailed binaries. So it's mathematics is called a stochastic differential equation. And one can assume the noise is with a zero mean and it's a Gaussian, and it's a white noise. Well, what we found in biological process actually turned out is that we found out this equation is equivalent to following one, and with a scalar function, that's a gradient. So that's every physics can recognize this to be the force, and with a symmetric matrix defined by noise here, and anti-symmetric matrix. So basically means every stochastic process, like in the form of a stochastic differential equation can be cast into a form with an energy-like function. One can actually show if steady-state distribution function exists, and the distribution function is given by the expansion of the h function divided by epsilon here. So let's have a precise the form of Boltzmann-Gibbs distribution function. So in a way, satisfy every requirement of formula physics. So the question is, can one really do the transformation from S to N? The answer is yes. So formally, just one page. Since those two equations, S and N, are equivalent, I can eliminate the velocity. I got this algebraic-like equation. Simple. And now, since if I look at the equations on both sides, let's have two parts. One is smooth function, like a f, or gradient of energy function. Another one is noise, which is highly kind of very violently. Okay, so I can make further assumption. The smooth part function that can equal to smooth part, and the noise part can equal to the noise part. Okay, so this I think for students come out from Tony's group, will feel this argument is reasonable. Is that the noise part we know typically come from a bus, and the bus experimentally maybe is one kind of tune it. So you can switch the bus on and off. So that means those two sides equal to each other is reasonable. So once you get that, okay, then we can proceed from those two equations. First, it's the well-known potential condition. The gradient of the curve of gradient function should be 0. It's a potential function condition. So get this. That's antisymmetric matrix. Oh, sorry, it's antisymmetric matrix with element 2 is n times n minus 1 divided by 2, and the second one is what we call the generalized Einstein relation. In the following way, we allow each side to times its transpose, then do an average. By definition, this will be S. By definition, there will be D. So it's a generalized Einstein relation. So once you got that, have a way to solve this, then solve S and A, then you have doing the integration, you get H, so you complete the mapping process. Well, there's some check. The first check is that in the zero noise limit, the H is indeed, one can check, is the operator function. Further, if the friction is 0, then one can check, then let's recover the Hamilton equation. So it's then we combine to our unknown physics. So that means we are on the right track. Well, there's some other check. So it's kind of my time is running out. There's one can check like a typical dynamic system whether this construction can be valid or not, like a chaotic system. The answer is so far. For those cases, we can do this even analytically. So I just pass this. I want some numerical way to find out the construction. I think I want to come to the point. This new structure is not purely on a mathematical level. Actually, it allows us to have new predictions. And there are 3 of them I think is highly non-trivial. One is what I call the generalized Einstein relation. This S plus A times D and times S minus A equal to S. And the original Einstein relation is in one dimension. In one dimension, the anti-symmetric matrix is 0, so then we basically get the S times D equal to 1. So from here, you probably get a sense. The D is a diffusion coefficient. S is a friction coefficient. So the original Einstein relation just said the friction coefficient times the diffusion coefficient equal to some universal constant. It's independent of the details of the system. Now we extended this in a higher dimensional case, in a nonlinear case. And the interesting is that so far, to my knowledge, no experimental check on such a relationship yet. Okay, that's the first one. Second one is that the second assumption we made actually needed to a new stochastic integration, which is beyond Ito and Solotanovich. So beyond what the typical physicists thought would be the useful one. And that can be tested by experiments too. The third one is that with such a construction, we can extend the Jarzynski equality into situations which typically there's no definition of free energy. One can extend this. So again, this can be tested experimentally. And I just want to show, so far, there's one experimental indication show. For that experimental situation, it's not Ito process. It's not Solotanovich process. It's Ito, it's Solotanovich. That's the theoretical result is correspond to present case, and the red dot is experimental data. So basically show up is more close, new stochastic integration is possible. Okay, one can say more, but I want to end this with a perspective. If this is true, first, we have a new formulation of Darwin's evolution dynamics, freeze and days, evolution by variation and selection. To the best of my knowledge, any biological process satisfies this type of equation. But if you want to quantify this, then it's just the stochastic diffusion equation. And then, as we know, that's implied existence of a Hamiltonian. That means we have a canonical distribution, the Gibbs-Boltzmann distribution function. And this also means we need to update what this old way of S equal to log M. I think that's probably not general enough. And so the last point, if this is true, I think there's a way to answer Tony's question on quantum mechanics. And the logic conclusion is that by this is that the quantum mechanics is correct, but it's incomplete. Thank you. Happy birthday, Tony. Yes.
Time for one question. Yes, please.
So you said that cancer is not caused by mutation. Talking about causation in complex things is a little bit tricky. So if you operationally say that you say things are caused by mutations, if removing all mutations would have prevented the cancer, are you really, what fraction of cancers do you think would be present if all causes of mutations would be removed?
That's a good question. I think it can be answered in two opposite ways. First, one can check the data for some clinically defined cancer to see whether all the major cancer mutations, the cancer genes are mutated or not. And so now this has been done for some cancer, actually, for example, like leukemia. They could not find any mutated genes. So, but phenomenologically or clinically, that's a cancer. So it's one way. And the second way, that means even if we have a mutation in the cancer genes, you could still in the quoted normal healthy state. But for example, just looking at it from outside, every bit of it just looks like completely normal. So this also has been confirmed experimentally. Yeah. So you can. So that means mutation, from a mechanistic point of view, is not the real cause of cancer.
Yeah. Okay. Thank you, Pingao. I think that's all we have time for. Our next speaker is Rongji Tao from Temple University. The title is From Sustainable Energy to Preventing Heart Attacks and Strokes, Challenges for Soft Matter Physics.
Yeah, a little slightly different, but it's okay. I'm very honored to be invited to give a talk here. I began to know Tony about 20 years ago when I was in Carbondale, University of Southern California. Afterwards, we have a lot of discussion about physics. You'll see this is actually completely different from most other people talk. But Tony gave me a lot of discussion, help, and support. I later will give you a little bit of detail. So what we will talk actually is something related to the soft condensed metal, how to prevent heart attack and stroke, and also relate to this, the suspension, the sustainable energy. Okay, the work is, the group is here. It's basically is a physics, also medical school people. Okay, the first is, this is a well-known information. Heart attack is the #1 killer in US. Every time, basically in 1 in 4 deaths in US is caused by heart attack. Then if you add a stroke, there will be much more worse, okay? So this is a similar situation in the all other countries or industrial world. Now, what happened is heart attack happened to people young, old, and people with smoke or non-smoke, with high cholesterol or non-cholesterol. What happened is, so it's the more than 10 years ago, University of Edinburgh did the first survey. They surveyed about 3,000 people with heart attack. They found all of them had high blood viscosity. Later, University Chicago Hospital also did the same survey, confirmed it's all of them have the high viscosity of the blood. Okay. Now recently is found is turbulence, because this issue was quite new because people don't realize turbulence is a big issue because normally is turbulence you need a high Reynolds number. But what happened is the key is the blood vessel is not smooth because you have branch, you have plaques. Okay, so that caused a lot of problems to create a turbulence. So I will show you is so basically is what we need is we need to reduce the blood viscosity. Meanwhile, you also suppress turbulence. That's the key to prevent stroke and the heart attack. Now, little bit unfortunately, what happened is these two tests conflict each other. Okay. For example, it's currently the only way to reduce blood viscosity is to take medicine. But if you take medicines, blood viscosity is reduced, then you calculate Reynolds number increase. So that means the turbulence is getting worse. Okay. So in addition, currently there's no medicine, no any methods to suppress turbulence in blood flow. So this is we really critically needed a new science and new technology. Now this same issue happened to the energy part. So for example, this is the pipeline from Alaska to California. So because the viscosity getting higher, so they heat it. This is the famous the heater station in China. Every like 10 miles, there's a pipeline, there's a heater station. In addition, like if with the offshore crude oil, the viscosity is very, very high. So you need to reduce the viscosity. The currently very much depends on the heating. But what happens is the Reynolds number increase. Turbulence is getting much worse. So that's the problem. That's the problem. In addition, heating is not efficient. Also create an environment problem. So a couple things I need to mention about turbulent flows. First is the turbulent flow will be required to transport same blood, same flow rate. You need a much higher powers, okay, pump powers, because what happens is the friction factor is completely different. The second is what happens is in addition to that, if you have turbulence, the shear force on the tube is much higher. So turbulence could easily rupture the blood vessels. And that's one way is an important factor to create a stroke. Then in addition, what happens is this is the wax on the pipeline. Okay, what happens is if your oil flow is turbulent, particle is everywhere, so then you easily create a wax deposition on the wall. Similarly, if you have the blood flow is turbulent, disturbed, they create a plaque inside the blood vessel. If you have laminar flow, situation will be different. Okay, so that's important things. Now, in addition to that, the turbulence is an important thing. Like Feynman said, the turbulence is the most important unsolved classical physics problem. Heisenberg said similar things. So these are have very important basic of science. Now, what happened is we realize it's from soft condensed metal, in solve these problems, we need to have anisotropic viscosity. So what happened in order to reduce the flow resistance, we improve the flow. We want to reduce viscosity along the flow direction. But in order to suppress turbulence, we need to have the viscosity higher in the direction perpendicular to flow. So then you don't have such motions, turbulence is completely suppressed. So we need to create viscosity anisotropic in this way. So first thing is we did it with crude oil. So how you can create a crude oil anisotropic? Because crude oil is a liquid suspension. You can consider either the wax particles or the asphalt particle suspended in the base liquid, which is the diesel or gasoline. So what happens is they have different dielectric constant. So along the flow direction, we apply strong electric field. So the particle polarize, they form short chains. Once form short chains, the viscosity becomes anisotropic. Along this direction, viscosity is tremendously reduced. But in this direction, viscosity is getting very, very high. So turbulence is suppressed. Afterwards, it becomes laminar flow. What happened is because we tried this methods, but what happened is we did all try other possibility, couldn't verify experiment. So eventually we did the neutron scattering, which verified the chain formation. Okay, so this is before the electrical field applied, particles are random distributed. Then you can apply electrical field. You see the chain structure coming. And from these, it's the gradually form the structures. Also in laboratory, we can also very quickly verify the viscosity reduction. So it's this crude oil and gravity, it's go down. So if we turn on the electrical field, apply the electrical field, then initially this is the cup connected to the mass flow over here. Then the flow rate, the slope is the flow rate. But if you turn on the electrical field, the flow rate is increased about 7-8 times. Like this one is the viscosity eventually reduced 85%, and the flow rate increased 600%. So the end is this technology is about 100 times efficient than heating. I will show you the test the suppressed turbulence, because this will show you how important is suppressed turbulence. This was we tested in the 2014 in the Keystone Pipeline. We tested is right over here. This is the Keystone Pipeline phase 4, and at that time later was vetoed by Obama. So our test is right over here. Then this is a device. So the oil is coming, then spread to 4 cylinders. Inside the parallel is the mesh electric, so apply electric field. The oil flow over here, they're coming back to the pipeline. It was surprising what happened is once this is the monitor the pump power. So what happened is when the device turn on, the pump power is go down go down very, very quick. So the people, the Keystone Pipeline engineers were shocked. So I was outside, they immediately called me back, said, what's wrong with that? I said, how could it be, is anything wrong with the monitor? So I told them this is not wrong. It's the showing is the turbulence suppressed. So I immediately showed them the calculation. So this is from the pump from starting over here to next pump. Then once the oil gradually laminar flow is suppressed, pushed from the treated oil become laminar flow, then this is turbulent flow. Then pump power you can calculate. One is for laminar flow, while this is for turbulent flow. Then you find that the pump power will reduce even until the minima to the whole section become the laminar flow. So if you compare this one, then everything is consistent. It's the same shape. So what happens is turbulence, if suppressed, the pump power is reduced 72%. So in other words, is the pump power of the turbulent flow, it's increased by 360%. So this is if it happen to blood flow, that's how much power needed for this, how much workload for the heart. Okay, so now let's coming back to the blood. So how we can reduce the blood viscosity, also suppress turbulence? We need a magnetic field. What happens is the blood is a suspension, liquid suspension. 40%, typical people have 40% in our red cell. Then in the plasma. The red cell contains iron. That's responsible to transport oxygen. We already know it's because of these iron molecules. The red cell is paramagnetic. Okay, so then it's if we apply magnetic field along the blood flow direction, red cell form short chain. Initially, red cell random distribute. They form short chains. The polarization along diameter direction. So it's form the chain in this direction, this way. Then we can calculate. So we can calculate the viscosity. Once the form the chains, the intrinsic viscosity along this direction is reduced. In this direction, increase. So initially, like viscosity roughly is relative viscosity is 7.6. Then after the magnetic field applied, the viscosity will down 25%, down to 5.6. But in vertical direction, perpendicular direction to the flow, viscosity increased more than about double. So then its turbulence can prove in flow is improved. So this is the experiment laboratory. So we're showing is the blood is flow down, then go to this cap. Initially, the blood is flow very, very difficult. Then after magnetic field turn on, the viscosity tremendously reduced. So the viscosity is reduced for laboratory test 86%. And the initially viscosity a little bit higher because what happened is we at the room temperature, 29.9, they're down to 3.6. Then I will show you, also show you, this is a technology confirmed is a suppressed turbulence. So we made this device, go over here, make like blood vessel, but it's not smooth. So we create a turbulence, then turn on the magnetic field. So then you will find it's different. Yeah, you see the flow over here. The flow goes this direction. This is under microscope. You see the red cell actually moving, deviates. This is not a full-scale developed turbulence, but it's the disturbance flow. Let's look at this one. Once the magnetic field applied, it's completely different. You see the become laminar flow. Even we have this plaque over here, didn't create a turbulence. So another thing is some people will ask, once you apply how long this effect lasts? So basically is as long as the short chain existed, the effect will be kept. So in laboratory we did is, we found it's one treatment, this effect lasts about 24 hours. Okay. Then similarly, we did a test with crude oil. This is a test on the DOE pipeline test field. So it's basically this is the oil goes circular around over here. So then on the pipeline we're showing treated. It's moving like more than 11 hours. What happens is that for blood, red cell is a little bit big. So if we form the laminar flow chain, the Brownian motion is much less effect to disrupt the chain. So effect for blood could be kept longer. The one thing is I want to tell you, it's because I mentioned about this one, the cigarette effect. So cigarette is found is if you have laminar flow, for liquid suspension, particle will move to the center, will not go to the wall at the edge, because on the edge they have the shear force is highest, middle is the lowest. So this is the effect already used on the pipeline to reduce the wax deposition. Then so what happened is we believe the magnetic field could be suppress the plaque in the formation in the blood vessel. So we did it is with mouse. Okay, so in about 1 year ago, we selected 10 mouse. Then I got the magnets. Okay, so all of them have surgery. 5 of them put magnets next to a jugular vein. Another 5 have put the same metal but non-magnetic. Okay, so it's a 5 mouse with a non-magnetic metal, 5 mouse with the magnets. So after that we feed them special food. Okay, so they grow fat to develop heart attack. So then what happened is that the situation is different. The mouse with magnets the blood pressure is low and didn't get very fat. It's a little bit fat, but didn't very fat. So, but what the mouse with non-magnetic metal become very fat. So then in the end of August, we sacrifice them. So check the artery. So the big difference. So the mouse with metal found it's the cross section here. It's the main thing is here is usually have developed plaque to develop heart attack. So the plaque is about 20% area cross section is blocked. But a mouse with here, it's about a little bit 6% blocked, so almost nothing. So big difference. So this finding is make a medical school excited. And now it's about three groups is working on the mouse. They told use slightly different methods. Here is use surgery, so later they use the ring magnet put on tail. All of them told is working. Okay. So this is, we later also check the blood. So check the blood, we found that the chemical position is almost same, okay? So all of them high cholesterol, But we check the viscosity, blood viscosity. This red one is the mouse without the magnets. So that's the typical viscosity of mouse. But the mouse with the magnets found is along flow direction, viscosity about 16% lower. But in the perpendicular direction, viscosity much higher. So that's make the blood flow is laminar. Okay, so this is so it's clearly cigarette effect prevented the plaque development. So in addition, what happened is this is we already found this magnetic treatment will improve the oxygen function for blood. The main reason is there's a disease called Rayleigh. Okay, this is like Africa, 30% of population have this disease. So basically, red cells attach each other in this way. So the surface is blocked for oxygen function. But if we apply magnetic field, they polarize. Once they polarize dipole in this parallel direction, so they break from this short chain. Afterwards, all the surface full functions. We already found it's working, and showing is the oxygen function will improve. Recently, we began to do clinical trial because because what happened is to make this such technology to medical application, you need 3 steps: lab test, animal test, the clinical trial. So I apply the clinical trial. Then initially is each university has RRB, Institution Review Board. So they gave me a little bit difficult. They said, you are physicists, you want to do clinical trial. We only allow doctors to do clinical trial. Then fortunately my group has some doctors, okay? So then they always delay. Then I send my protocol to FDA. Fortunately, the FDA reviewed and gave me strong support. So they send me emails, claim this technology will be safe for test clinical trial. So I showed the email from FDA to the RRB. RRB said, email doesn't count. We need a formal document. So then I request FDA, give a formal document. FDA eventually sent a formal document. So then it's in December, we got approved. Okay, so began to do clinical trial. And so the effect is, first is we're showing the blood pressure will be lowered. So that can help the people with hypertension. Second is the turbulence is suppressed. So some people has a heart murmur, the sound will be disappeared. The third one, the blood oxygen function will be improved. Then also we should find the about effect will last for more than 24 hours after one treat. Then if we have continuously therapy, that will prevent the plaque development. Okay. The clinical trial is still going on. The results, what happened is RIB said you cannot test all of these at once. You have to step by step. So the first clinical trial is try to reduce the blood pressure. Okay. So then he said afterwards you can try the suppressed murmur oxygen function. You have to do one by one. Of course, the blood pressure, reduced blood pressure is one important, probably the most unpopular thing. So typically the clinical trial is to do this way. So the subject coming, first measure the blood pressure, then put a right arm. This is a device we modified. So make the magnetic field parallel, so its blood flow along the arm direction, flow along this direction, the magnetic field parallel to the blood flow direction. So then they put on inside of this hole for 10 to 15 minutes. Meanwhile, we monitor the blood pressure. Then afterwards, after treat, so coming back 24 hours, we measure the blood pressure again to see how long the effect lasts. The results is wonderful. To be honest, it's much better than I already expected. So first is 100% working. This is a typical example. This guy coming is blood pressure is 150/88. So then it's the, once his arm put inside, 11 minutes down to 111.70. Then after 24 hours, he coming back, his blood pressure is 129.78, showing it still have effect. Then we already tried the more than 60 people tried. Everyone is the same, okay? Then what happened is this technology also, several people thank me, saved their life. This is one falling, it's the lady, she is a doctor, pediatrician, before Christmas coming to Philadelphia to see her son. But she has high blood pressure. Then she used medicine every day. But somehow she said she couldn't find her medicine after flight. So then it's after 1 week, she was terrible. She was asked for moving to emergency room in hospital. Then her son was somehow take the course at the Temple University, heard my technology, so called my student. So they immediately had a treat. Then after treat, her blood pressure getting normal. So then afterwards, after treated 3 times, then she looked like everything's fine. So then afterwards, she returned to her own country. She thanked us for saving her life and avoided heart attack. There are more, and we also have one faculty member. He had the heart, almost died by heart attack 6 years ago. And afterwards, he's still under recovery. He takes medicine every day. Then before Christmas, somehow miscommunication between the pharmacy and his nurse. He didn't have medicine. Then he got terrible. So he came into my lab to have a treat. Then after treat, he said, oh, this is much better. Said, my eye is bright and feel much, much better. So he later told me that because he's taken this medicine, he had a side effect, blood bleeding. Even urine has blood. So he doesn't want to take medicine anymore. So he said, could I come to your lab, like have a treat every day? I said, you can, but you need to talk to your doctor, see whether it's okay. But the doctor was giving him okay. So he treated, and treated about two months. Then his doctor checked his heart. Said, it's surprising. Said, your heart is much better. Because initially, because during his heart attack, some muscle didn't work. He said, your heart muscle is coming back. So he's very excited. And then also some students, they had high blood pressure, said, I saved them. And they come in to have a treat about 1 week, said it's gone. The one policeman coming to treat. Then he said, after treat, he said he used to have pain in the neck. Then after treat, the pain neck disappeared. He's so happy. So in any way, we are still at a treat, but it's very, very, very exciting. Second is that we also did somehow placebo effect. Of course, it's FDA, it's specified for device, you don't need to do the placebo effect. It's slightly different from medicine, okay? But we try it. So there's one day we have a person coming with very high blood pressure, 173. So this is the risk area. But he said he used to be not so high. So I asked him calm down and put the arm inside, but we didn't turn magnetic field on. Then actually his blood weight didn't go down. So actually even a little bit go up. So then then we decided to turn on the magnetic field. Then in about less than 10 minutes, go down 112.75. So it's showing this is very, very effective. I come into I want a little bit of mention about Tony's help. So when I'm working on this problem, I have a discussion with Tony. Some people showing the Tony's handwriting. I was lucky I have an email from Tony. This is an email from 2005. Tony is reading my manuscript, discuss with me. One important thing is I had a discussion, even 2007 or 2008, I don't remember exactly. Tony and I discussed about this one. Tony asked me, maybe you need to look at the pneumatic liquid crystal issues. So then I look at the pneumatic crystal issues. Then it's found when pneumatic liquid crystal align the one directions, flow direction, along viscosity become anisotropic. Along this direction is reduced, in this direction increase. So that's Tony's discussion, very helpful. Okay, so let me conclude my talk. Yeah, so what we found is if we basically is for this important problems, it conventionally doesn't work, but we need to make viscosity anisotropic. Once we make viscosity anisotropic along flow direction, viscosity reduced, in perpendicular increase, turbulence could be suppressed, the flow become laminar, and the lab test and the mouse test, this is a magnetic field working for blood. It's also the clinical trial all confirm this new technology will work. So finally, happy birthday. Thank you, Tony.
Okay, one quick question. Yes?
Have you thought about the possibility of using superconducting magnets, high-temperature superconducting magnets?
Yes, actually is what happened is we have the visitor from Taiwan, but they are very important person in Taiwan. I didn't know that. It's the it's diplomat. So they have high blood pressure. Then tried. Once tried, it's immediately reduced. So they are so happy. So now they go back. The two Taiwan companies, they claim is the world's largest manufacturer of the blood pressure monitor. So yeah, I coming back. So it's
Tested how high, what kind of a function of magnetic field the effect is.
yeah, it's yeah. We,
Big effect, and how high can you go?
yeah, it's the magnetic field. Currently, magnetic field we use about 1 Tesla. Okay, that's I did a little bit of calculation. What happened is from the susceptibility, then it's the time is the magnet inside the magnetic field. We figure about 1 Tesla. If a little bit higher could be better. The question is unclear. If too high, whether could it be chain get too big? That's any problem. At this moment, we don't know. But it look like 1 Tesla is working nicely. Okay, so that's I put you look at the 3 red cells joined together. I didn't want to go, yeah. But I already talked to 2 companies. They are interested in manufacture. One is the superconductor companies at the APS March meeting. They are very, very interesting. They are willing to manufacture a device for us. Then another one is the manufacture electrical magnets for us. Yeah.
Okay, I actually, so, okay, please, just one last.
People go into MRI machines all the time.
Yeah.
They've never noticed any change in blood pressure of the patient going in an MRI.
Okay, I tell you because what happened, Paul Cho is very interested in this one. Then he raised the same question. I told him because what happened is MR, because you have a number of places apply MR, it could be perpendicular, not parallel. So I predicted blood pressure will be slightly higher. Then afterwards, leave the MR, blood pressure will be getting normal or even slightly low. It goes this way. Then he did a test, confirmed this, my prediction. Okay.
Okay, thank you very much. That was a great talk. Our next speaker is George Crabtree, and he's going to tell us about critical currents by design.
Indeed. Thank you.
Thank you.
Thanks so much. That's it. Perfect.
So, what a pleasure to be here and what an honor to help celebrate Tony's 80th birthday. I feel like I'm meeting Tony all over again. I've known him for about 30 years. He and I were both in a high-temperature superconductivity STC sponsored by NSF back in the 90s, and had lots of interaction then. Very consistent with some of the other talks we've heard. I ran into Tony all over the world, Grenoble, lots of other places, and we had some very good discussions there. But I'm surprised to learn that he's so knowledgeable, speaks 3 languages, including Latin, and has done so much work in science. So this, to me, is quite a revelation. So Tony, my congratulations especially. So I want to talk a little bit more about superconductivity. We heard yesterday a lot about the theory and the mechanism and so on. I would like to talk about another feature, the vortices, which is the thing that makes the superconductor superconduct. That is, why does it have 0 resistance in a magnetic field? And I want to talk about a new way of looking at the vortex ensemble and predicting its behavior as a large collective object. This is something you could think about 10 years ago. Until about 5 years ago, you could do nothing about it. Now we have a thing which we've always had, time-dependent Ginsberg, Landau, but we have big computers that can really model exactly what happens in the vortex system. That's the big news, and I'd like to tell you about how that might actually change the way we think about vortices. So, first want to acknowledge lots of collaborators. In fact, they've done most of the work, and most of that is at Argonne National Lab. This is on the right, you see a picture of a vortex. So it consists in a magnetic field of a normal core. That's the red thing. Let's see, I think I can, yeah. So here's the normal core. Here's circulating supercurrents outside the core, and they gradually fall off along this penetration depth. The core has a size about the coherence length, and that is a spontaneous emergent sort of structure that when you put a magnetic field on automatically comes out in type 2 superconductors. That is the thing that Abrikosov discovered, in a sense, theoretically, in the 1950s. He discovered it whole cloth. It's virtually unchanged since the 1950s, and indeed, it controls almost all the electrodynamic properties of superconductors. So quite a wonderful scientific triumph from more than 50 years ago. But that's the thing that we now understand much better. So if you'd like to read a little bit more, here are a couple of papers that really go into detail about what I'm going to talk about. Everybody knows this picture. So this is Kamerlingh Onnes in 1911 at the discovery of superconductivity, and there is the resistivity of mercury, which very surprisingly went to 0 at 4 degrees Kelvin instead of continuing on. There were other predictions. People expected it to either end at a finite resistivity at t equals 0, or at 0 resistivity at t equals 0, but nobody expected that it would fall to 0 above t equals 0. So that was 1911, a big mystery. There have been 5 Nobel Prizes which relate to superconductivity, starting with the discovery. And of course, the famous BCS, the prize came in 1972, well known around here. Tunneling, we've heard a lot about that today. The high temperature superconductors in 86. And this Nobel Prize, a very interesting one in 2003, Alex Abrikosov for discovering vortices, theoretically. And Tony, whose Nobel Prize was not about superconductivity, but helium-3. But as we've heard, he could have been recognized for many other things. I might point out that some very famous physicists attacked the problem of superconductivity, Einstein and Feynman, 2 of them. They couldn't do it, and it was Bardeen, Cooper, and Schrieffer who finally did. Very much like that, Tony has done so many things, you could imagine lots of other things that he could be recognized for. So here I've already mentioned what the vortex is. So a normal core surrounded by superconducting supercurrents, which fall off with the penetration depth, which is typically long. The core has the size of the coherence length, and these automatically come out in the presence of a magnetic field. Fairly easy to understand what one vortex is when you have many of them, and as you increase the field, that results in many more vortices being created and their density increasing. That's how the field increases. Whoops, you have, let's look at this first. If the temperature is low enough, it turns out the vortices repel each other, repulsive interaction. They can form a lattice. In fact, not unlike a crystal lattice, except these are long, flexible objects. And if you do things like increase the temperature, then indeed the thermal energy can be big enough for this this lattice of vortex lines to melt. If you add disorder, you can make glassy states, which are still in the solid state. So these vortices undergo many phase transitions that look very much like atomic matter, and for that reason they're often called vortex matter. So I mentioned that it's the vortices that make superconductors superconduct. How does that work? If you imagine a yellow superconductor here, a magnetic field in this direction, and a current flowing in that direction, elementary physics, there will be a so-called Lorentz force on each vortex which pushes sideways, so perpendicular to the current and perpendicular to the field. If the vortices move, then it's a magnetic field represented by this vortex moving in a current. And that produces, it's Faraday's law, use your right hand, an electric field opposing that current, and that appears as a resistivity. So in spite of the fact that it's in the superconducting state, if the vortices move, there is a finite resistivity, and indeed, it's not lossless. So if you imagine the whole game then is to pin the vortices, put in enough defects so that to immobilize them, so they cannot move, and if they cannot move, then the resistivity suddenly goes to zero. Those defects, they could be nanodots, they could be sort of amorphous disorder of various kinds, second phases, dislocations, intergrowths, all kinds of defects. And if you imagine a sort of a simple pinning landscape, here's an example, large defects and small point defects, and it turns out these behave differently. That's something you might be able to simulate, or at least imagine that you could simulate. In a real superconductor that looks like this, it's a much more complex pinning landscape. There are points, there are lines, there are planes, there are second phases. It'd be pretty hard to simulate what that pinning configuration would do to the current. So that, in a sense, is the challenge. The lower right-hand side is the challenge. Well, there are lots of superconducting applications. All of them require zero resistivity. Here are some of them. So cables, you could imagine, replace all the electrical cables in the world with superconducting ones, get the losses down to zero. Offshore wind generators, turns out a superconducting generator or motor is about half the weight of a normal motor or generator. That's because you can put a lot more current through a superconducting wire than you can through a copper wire. Transformers, fault current limiters, lots of other things here. Many applications. The trick is to get a really high critical current. That is the highest current that the superconductor can pass without going normal. There's all kinds of wires. So you might imagine that back in the 1950s and 60s, we had niobium titanium that's here. This is a graph of the critical current versus the magnetic field. So, and these were the workhorses in the 1960s, really until the 1980s. When the high temperature superconductors were discovered, they had a much higher critical current, and they were much more stable in magnetic fields. So that's this group at the top, and there are a couple of things in between here. the point is there's lots of superconducting wires you can make, and the real question is how can you get the critical current up? So how good are the wires? Here's some of the applications that we talked about. Remarkably, the best superconducting wires achieve less than 20% of their theoretical critical current. We don't really know why that is. It's pretty easy to estimate the theoretical critical current, and it's pretty easy to measure what you actually get, and it's pretty easy to conclude that it's 20% or less. So that's a major question. Cost is the greatest barrier to widespread development, and you could imagine that if you could get the critical current up by a factor of 2, you would need a factor of 2 less wire. That would reduce the cost by a factor of 2. Very, very big deal. So there's plenty of room for improvement. And the question is, after 60 years of vortices, why haven't we solved this problem? So let's take a look. Here's the challenge. The complex collective interaction of vortex arrays. So let's think about everything, every way in which a vortex can interact. There's first long-range repulsion between vortices. So that goes like 1 over r. It's really long range. There's a long-range attraction between a vortex and a pinning defect. That can be as long range as the repulsion. There's elastic vortex bending, so they're not rigid straight lines. They can wiggle around and be flexible. There's energy involved in that. There are thermal fluctuations, which can induce some of these elastic bending fluctuations. Vortex cutting and reconnecting, so 2 vortex lines that might be at an angle, not because they're at a field angle, but because pins distort the directions. Locally, they come together like this, and they cut and reconnect, so what was the right side of this one becomes the left side of that one, and vice versa. There's an interaction with an applied current, and there's a temperature and field dependence of all of these things. So it's kind of easy to understand what one vortex might do. You can simulate that. You can simulate 2 vortices. That's a treatable problem. It gets tougher when you have many vortices and many different kinds of pin sites. 2 kinds of sites here, big pins and small pins. It gets almost impossible when you add a transport current and the dynamics to it. So this is the problem that we face. Conventional treatment, simulate each vortex line and its interactions with each pin site. So it's like atoms. So I've got so many vortex lines, I'll model each one and put in a structure for it. And you can put in the long-range repulsion. But the collective response requires thousands of vortices, and this is really a tough problem. It's reminiscent of the hydrogen atom by itself versus the solid or liquid collections of atoms. It's really a different magnitude of problem. So what do you do? Well, one thing you can do is use the time-dependent Ginsberg-Landau equation. And here's Albert Schmidt, who in 1966 proposed the time-dependent Ginsberg-Landau based on reasonable assumptions about how a static wave function described by static Ginsberg-Landau might evolve in time, analog to the Schrodinger equation. Turned out to be very, very effective and describes a lot of dynamic quantum phenomena. So these are the equations, not quite in the way Schmidt wrote them down, but this is a more recent paper by one of our collaborators, Sadovsky, written down this way. You put the pin sites in artificially by hand. So basically, you put a normal region into the superconductor, and that normal region attracts the vortex because there's a normal core in the vortex, and it lowers its energy by sitting over the normal region. So that's a way to put in by hand an arbitrary sort of array of pin sites. So the advantage of the time-dependent Ginsberg-Landau, it's phenomenological, not mechanistic, so you won't get any deep insight about what's happening to a given vortex, but you will be able to understand exactly what each vortex does, its dynamics. It describes all the superconductors in terms of a coherence length and a penetration depth, So these are phenomenological parameters. You really don't have to know anything about the material you're dealing with. You choose sort of empirically these two characteristic links, and that describes the system. It's a continuum theory, so you can solve it on a grid like this. You're solving for a wave function, basically, or an order parameter. The zeros of that order parameter define the positions of the vortex, each vortex, so you can see how they move, where they are. You can watch how they may wiggle in space. So this is really an advantage. You're solving for one parameter. You're not solving for each vortex separately. The static version was enormously useful. We know that from when it was first proposed in the 50s. Dynamic version, I say here just coming into its own because it's only recently that we've had computers big enough to make these sort of massive calculations and see what happens. So the advantage, you treat the dynamics of very large vortex arrays, thousands of them. All of the interactions are included automatically. You can put in multiple kinds of pinning defects, so you can put in a normal region as a point, as a line, as a plane, as a macroscopic second phase, whatever you like, and you can mix them up, put them all in at the same time if you like. And you get out something quite remarkable. You get the macroscopic behavior of the vortex array as a function of current and resistivity and all kinds of things. But if you like, you can look on a much smaller scale, same calculation, same simulation, and get the behavior of one vortex. So this one treatment goes from nanoscopic to macroscopic. It requires very large computational resources to do 1,000 or 10,000 vortices. And there are really two eras to this. From 1995 to 2012, that was the early treatment of tens or maybe hundreds of vortices limited by computational resources. Since about 2012 till now, you can do a much larger scale treatment of thousands of vortices because we have the computational resources. So this opens up a very new way of looking at the vortex system. So a couple of examples of what it can do. Here's the vortex depinning from a single large spherical pin site. This is the pin site. Here's the vortex line. Here's the Lorentz force. So here's the magnetic field. The current would be in this direction. Point is, as you see, as you increase the current, the Lorentz force on the vortex line increases. It wants to pull away. It gets distorted from this pinning site, gets distorted more, and finally breaks away altogether. That's something you can see in detail. In fact, this was done with a time-dependent Ginsberg-Landau simulation of a single vortex. You can look at mixed pinning landscapes. So here's an example where there are two kinds of pinning sites. The first kind is shown in this picture. So these are nanorods on the vertical direction here. And you might expect that as the magnetic field aligns with those nanorods, that the pinning strength would go up. And that means the critical current would go up. And indeed, that's what you see. So as a function of magnetic field angle, here's a peak. That peak corresponds to when the field is aligned with these nanorods. And very surprisingly, if you add by irradiation, this is with lead ions, heavy ions, at 45 degrees, you introduce lines, again, linear defect. You might expect that as the magnetic field aligns with those lines, that the critical current would go up. And then as you go further and it aligns with the nanorods that were there originally, there would be a second peak. That is not what you see. You see only a single peak. And the single peak is due to the irradiated columnar defects which were put in after the nanorods were there. So this shows that the vortex complex pinning landscapes don't have to be linear. So they may not add linear, and this is a rather dramatic example. Here is a time-dependent Ginsberg-Landau reproduction of non-additive pinning, and you can tell from this this simulation. Why actually it occurs, let me not go into it, but if you're interested, take a look at this paper, which was published about 1.5 years ago. So, in fact, here's the explanation. The vortices slide from one nanorod to the next along the columnar defect. So, a dynamic sort of phenomena that nobody had expected before. Here's another example, simulating complex vortex and pin-side arrays. So the top picture is a 3D tomographic mapping of 71, exactly 71, nearly spherical nanoparticles ranging in size from about 10 to 100 nanometers in diameter in YBCO. And this was an actual electron microscope picture. So the idea was to do a time-dependent Ginsberg-Landau simulation of exactly that experimental situation, putting in by hand pinning sites of the right size in the right position that exactly mimics what was seen in the sample. And on the right-hand side, you see, as a function of field, the critical current for a certain direction. The experiment and the simulation are almost identical. So this gives you a pretty good idea that indeed the time-dependent Ginsberg-Landau approach seems to be reproducing reality. So here's the opportunity. Large-scale, complex 3D vortex pin-side simulations. They've arrived. They have not been fully, by any means, exploited, but I think we've shown that indeed they can be done. Things like vortex repulsion, pin-side attraction, elastic flexibility, thermal fluctuations, cutting and reconnecting, interaction with the current, and the field and temperature dependence are all included because that's in the Ginsberg-Landau equations. The time-dependent Ginsberg-Landau, it's a kind of a vortex genome. So we've heard about the materials genome for atomic systems. This is an equivalent genome, perhaps even more powerful, because it goes from the nanoscopic to the macroscopic with one simple simulation. And so this is the analog of what you might get for atomic material. So it allows us to ask fundamental questions. Why is the practical critical current limited to 20% of the theoretical limit? This may have to do with the nonlinear addition of complex pinning landscapes. As we saw earlier, a second pin site eliminates the pinning from the first one. That's totally unexpected, and it sort of says it's not obvious that more is better. You have to actually think about what kind of pin site you're putting in. What makes the pin-site interactions destructive or constructive? So we found an example of a destructive one. Wouldn't it be better to find some constructive ones? So supralinear pinning addition. And what are the guiding principles that control the vortex behavior? So this relates in a sense to Tony, although he's not known as a vortex scientist. But this opens the kind of new door that I think Tony has shown us can be opened in physics when you think deeply about what's going on and think critically. So with that, Tony, once again, I may be the last one. Happy birthday.
Questions, please?
The image you showed of those polymer defects
Yeah.
gives the impression that it is so crowded, this defect, that I worry about other limiting factors to your critical current. Just the fact that the current has to pass through a boundary somewhere, for example.
Yes. So, I mean, that's a good point. So one implication of that statement is that the more defects you put in, the more normal regions you're putting in, and the less superconductor you have to carry current. It turns out that's automatically included in the time-dependent Ginsberg-Landau. So that's another feature that you get for free. What happens in that experimental, I agree, that was a very dense set of nanorods. And we haven't tried to look at exactly what would happen, let's say, if you had a lower density. But your question's a good one. Yeah.
Yes, please.
Yeah, two technical points. How do you simulate the pinning sites exactly? Are they boundary conditions on the side? Or how do you implement that in a simulation? And the second question is, what's your resolution in your grid?
So I would have to look at, for the second question, I have to look in the paper. I don't know, but we can easily look it up. And I imagine that it varies, that it's not always the same. So how do you put the normal state in? It's simply a variation, a continuous variation of TC. So it's, but think of it as condensation energy. So as a function of space, you can vary continuously the condensation energy however you like without a boundary. It's a smooth variation, but it seems to have the right effect.
You didn't say anything about the surface of the superconductor. You know, usually vortices rush in from the surface.
Yes.
And would that, how much of that could explain this discrepancy with the theoretical limit?
That's a good question. I would say we haven't looked at that. So that remains to be looked at. There's no reason why you can't put a surface on your superconductor and do a time-dependent Ginsberg-Landau, and in fact see that, that vortex rushing in and how it would change. Great question, and that's our next grant.
I think we have, did you have a question? Okay, if not, one last question.
Do you see any, or have you investigated any, for Coulomb defect, one set of Coulomb defect, any naturally sort of increase in the critical currents for matching field?
Say again, if we increase the magnetic field, does the critical current go?
B sub phi, you know, the density of Coulomb.
Oh, I see. Yeah, in fact, one does see that effect. And we have it here. So we didn't do as a function of, I didn't show you as a function of B. But indeed, you see, if you're below the matching field and above the matching field, there's a little kink that happens in the critical current, which is for exactly the reason that you said. Yeah.
Okay, thanks so much, George. Okay. Our last talk of the day is by our very own Philip Phillips. And the title, oh wow. It's a summary. Summary is, what is the summary, Phillips? Leggett summary. And he's going to take precisely half an hour. Precisely.
Oh, I see.
Yes. Philip?
Yes.
Precisely half an hour. I've been instructed to tell you.
Well,
At the risk of missing reception and dinner.
all I will say is I will take no more than half an hour.
Okay.
But probably quite a bit less than half an hour. So, how do I summarize a meeting for which I've attended less than half the talks? That is what I'm attempting to do. The reason why I'm in this unfortunate position, so I entitle it Remains of the Day, is that for me this meeting began with quite a bang. I was involved in a car accident on Thursday around 5 or 6 o'clock or so, and I've spent most of yesterday and this morning trying to get a reasonable resolution of this problem. Anyway, and what's interesting, everyone in the department knows I had the worst car possible, and I finally got a new car, and this is what happened to it. Okay, so maybe a year or two ago, I received this note, topics for 80th, and this is Tony's handwriting, saying what he wanted for his 80th birthday. So there were a couple of choices. One was reflections, but Tony is incredibly forward-leaning. So he said, I don't want that. That's for really old people. What I want is a conference that talks about the leading problems in the field. Okay, so we've heard a lot about some of these problems, so I'm just going to focus on just a couple of them. Okay, one of the problems we've discussed is the Coop rates. And I started interacting more with Tony once I started working on the Coop rates because of the following quote. Regarding high TC, I think it will turn out that P.W. Anderson will have asked precisely the right questions, but will have given exactly the wrong answers. Okay, you know who said this? Tony. Okay. And when I read this in the journal, I went to Tony's office and I said, Tony, you sure you want to say this in print? I mean, what about Phil? I mean, he's going to come after you. And Tony said, I don't really care about that. Then I realized Tony had incredibly large cojones. And I decided that Tony was my kind of guy. And so it's actually because of this, Tony, that I feel this bond with you that I try to emulate. Okay, so anyway, the cuprate problem still remains the key unsolved problem. I'd say one of the key unsolved problems, probably the hardest problem in our field, and it's because of the strange metal. It's not just starting with a Fermi liquid and you end up with superconductivity. There are an infinite number of theories of, down here, but essentially of order 0 theories up here. Okay, and this has led a lot of us to think about how we might resolve the problem. Now, let me just point out the sort of key characteristics one is trying to address when you look at the strange metal. One is T-linear resistivity. The other is discovered by Dirk van der Marel, this omega to the minus 2/3, this mid-infrared optical conductivity, which Tony has thought about a lot, and that's where our work really overlaps, and the violation of Wiedemann-Franz. So explaining this collage of data is really the key thing that you would say you're trying to work on if you are explaining the strange metal. Now let's look for a moment at T-linear resistivity. T-linear resistivity has been described by some as Planckian dissipation. Because if you just combine the basic constants, you end up with a scattering rate that doesn't allow you to put in any other energy scale. It's just pure dissipation. It's the largest dissipation possible. Now, we've heard a very nice talk on quantum gravity, and many of us are trying to understand, is there some fundamental relationship between Planck scale physics and this, Planckian dissipation? And this is in the guise of the ADS CFT conjecture, our best understanding to date of quantum gravity. One of the things that has come out of that is that possibly it might require a new theory of electromagnetism. And Professor Briggs had a very nice quote in which you should definitely be worried if you violate the second law of thermodynamics, but if you have to give up Maxwell, that's just fine. Okay, so I don't think it is sort of heresy to say that you've given up Maxwell, and certainly that is my solution to this problem at this point. One of the, another overlap I've had with Tony is in the measurements in trying to understand this saving of the Coulomb energy and this mid-infrared. This is a very nice paper published in a very nice journal, very expensive journal. And one of the key things Tony said in this paper is something that we all sort of believe, that certainly the transverse and longitudinal dielectric functions can differ at finite momentum, but at zero momentum, they'd better be equal. They're certainly equal from everything we know, at least everything we thought we knew. And so Tony was very cautious about this, though. And he says here, for example, this has been shown in reference 8. Okay, so it turns out that you can measure, these are ellipsometry measurements or optical measurements, which in fact measure the transverse dielectric function. Okay, but an independent measurement of the longitudinal dielectric function in the normal state hadn't really been done until the very nice experiments of Peter Abamonte, hence one could address this question. Okay, so here's the new data from Peter Abamonte. He's doing momentum energy resolved electron energy loss spectroscopy And he's measuring the density response function. So the density response function is absolutely just related to the longitudinal dielectric function. And so from this you can extract this. And the key feature here is that within 0 to 1 electron volt, it's very featureless. Now you'll recall, so from this you can go directly to the optical conductivity. And, right, so this is measuring the density response. And if you look at what is seen by Dirk van der Merel in the mid-infrared using optics or ellipsometry, which is the transverse dielectric function, you see this omega to the minus 2/3. And that's not what you see over here from Peter Abamonte's data. So in fact, it seems as if the two are not equal. So we have written a paper with the experimentalists about the inequivalence of these two limits in the cuprates. And we've discussed this extensively with Tony. He's very shocked by this result, as anyone should be. But it seemed like there's something even weirder happening with the cuprates than we thought. It's being sent to PRL, for which it seems like all battles turn into metal echoes saluting a rusty shadow. Anyway. Okay, now one of the other things that came up in the context of the cuprates is bilayer graphene. And I wasn't here for the talk, but I'm told that this came up. And one of the things that has been discussed is what's the relationship between bilayer graphene and the cuprates? And are the two equal? And certainly a realistic question. The key point with bilayer graphene is what's happening at these, as you twist the layers relative to one another by a fairly small amount, and you see these dips in the conductance. And it's these dips in the conductance that's gotten everyone excited. Is this a new kind of insulator? Okay, now this didn't go down to very low temperatures, 0.3 Kelvin, which is certainly not low. If you go low, you'll in fact see that this in fact is not vanishing. Okay, now this is the phase diagram that has come about. And right at these dips, people are saying this is a Mott insulator. And as you go away from these, as you change the density right away from these magical points, you end up with a superconductor, and it has a dome just like the cuprates. So the question that arises is this an artificial platform for studying cuprate physics? I thought I would mention this now because this is a meeting where we're looking forward and other strongly coupled problems. So I just want to look at what's going on right here. Okay, so if you look at this scale for the conductance, in fact, the conductance is not 0 at the lowest temperatures here. So it's certainly not a Mott insulator. Okay, now the pattern that you have is this Moiré pattern at these magic angles, and that's given rise to a supercell whose dimension is given right here. Okay, now if you just go and calculate the number of carbon atoms or Dirac cones in sort of a unit cell of this, you'll find it's a very large number. It's around 13,000. Okay, now if you're going to, so if the argument then is that this is a Mott insulator, you then have to write down a tight binding model where you try to come up with localization of electrons in a 13,000 atom site. This seems fairly ridiculous, and I certainly would not think this would be the most natural starting point for this problem. So I don't think one could realistically think about these sorts of cells as being a platform for localized Mott physics. Okay, if you, however, look at something that seems much more natural, if you just look at what RS is, and it's in terms of this magic angle, and the densities are incredibly low in these systems, what you find is close to the magic angle, RS is in fact diverging. And hence it makes much more sense to think about this as a strongly correlated insulator of the Wigner kind, not the Mott kind. And superconductivity seems to be arising from doping or melting a Wigner crystal. And, sorry, let me go back. And if you just look at this formula, the magic angle is 1.05. So by that point, RS is basically infinite. Okay? So certainly by 1.06, you're well into the Wigner crystal. And one of the so my point then is that bilayer graphene, I don't think has anything to do with the cuprates. I think it really is a doped Wigner crystal. And somehow it's giving rise to superconductivity. And this is something I'd actually written a paper about many years ago. But this is still an unsolved problem. This is large RS physics. And that sort of brings me to the conclusion. If you were to try to come up with a common theme among all of these problems, is that this is physics all at strong coupling. And these problems are still unsolved. And hence it makes sense that Tony chose these problems. And I would like to add one more to that, this problem of bilayer graphene, which fits very nicely into all of the problems that are listed here as things that we can't apply the standard methods we like in physics, namely field theory, to go and find a solution. Okay, so that's all I really have to say, and part of this was supposed to be a sort of question and answer, or mainly just suggestions of other unsolved problems that you think might have been overlooked. So at this point, we can engage in that, or if you have any questions of what I've said, you could also ask questions about that. Do you have a question, Tony? Okay. And also, happy birthday. That's all was said, but you know, you're my colleague, so it's yes.
So these are not my work, but my understanding is the advanced structure calculations Alan McDonald did of the bilayer graphene case, that you have lots of narrow bands which are narrowly separated from each other, and the one that they claim is actually involved is actually flat.
Okay, so. So let me comment on that. The supercell contains 10,000 bands, and the lowest one of those has 2 electrons in it. Okay, right. Okay, so you do have a flat band. Okay, and at that point,
They calculated the effective U.
I certainly am very familiar with that. Okay, so I'm certainly well aware of that. The question then is, what is the U that was calculated is not an on-site U. It's a U given the size of that unit cell. These are what? I don't quite, okay, so they're Wannier functions consisting of a 10,000 atom unit basis. So, okay, so if your claim is that seems reasonable to form a Mott insulator, you can believe that. I think that's ludicrous.
I have a very naive question on this. So we normally think of graphene as not being correlated. You know, you can get these direct functions.
Right, certainly.
So I don't see where the
Okay, so, right, okay. This is physics that is in neither of the layers. It's only at it's only at these magic angles. Sorry. Yeah, it's only at these magic angles And at these magic angles, you can calculate the ratio of the potential energy to the kinetic energy. And here it is right here. In fact, this RS is taken directly from the data in Alan McDonald's paper. And there it is. Okay? So it's because this twist has created essentially a quenching of the kinetic energy that you're in a situation where the system is now incredibly strongly correlated. Okay? But you can't have this physics in either of these layers. Yes?
If RS is really that big, do you think that quantum oscillations can be observed? They were observed.
Okay, so they are not observed at the magic angle. They are observed once you dope the system and then you're above the superconducting dome. Okay, I don't know what the ground state is of a strongly correlated system or at least not necessarily the ground states. Apparently the ground state is a superconductor. But I do not know what the normal state is here. And certainly none of the methods that you have used in the past can access what's going on here. So it's some sort of strongly correlated metal. I don't know how you would, and I can't rule out that you would see quantum oscillations. Apparently you see them. But what is your question?
No, normally if it's very large RS, damping is large, so you don't expect to see quantum oscillations.
Yeah, but I mean, okay, certainly if you're in an insulator, I would argue that. However, if it's somehow a metal with a large RS, I don't know. I mean, there's certainly stuff moving around. Yeah.
So you can get flat bands by intrinsically localized nodes, things that can't move.
Right.
They can be two electrons sitting on two sites. The band can be flat because there's no kinetic energy, as you say. So I don't think it needs to be mocked. That's the first one. But at some stage, I'd like to take us away from this to another area, which is a superconductivity in the organics.
Right, right.
Where you see very similar effects. You see the same ratio of TC over TF that you see in
Right.
fluid rates, and their theories, as you know, since we both know the gentleman who
Right,
proposed them,
right.
where instead of the Wigner crystal, you have a paired electron crystal,
Right.
which was first proposed by Ashcroft a while back.
Right.
Comment on that, please.
I have no comment on that.
Well, that's another unsolved problem.
Right, yeah, that's another the organics are another very good example of this, Mott regime, or I would say it's not really the Wigner regime because you can form nice localized orbitals in that case, but
Actually, in the organics, you can show that the Wigner crystal is not right.
yeah.
What you had is instead of 1, 0, 1, 0 in the simple one-dimensional case, you have 1, 1, 0, 0.
Right,
It's proven
right,
that the charge density
right,
rate,
right.
everything except the superconductivity is understood.
Right, right, right. Look, I think the organics have been overlooked. I think they certainly exhibit Mott physics, and if you look at Kanoda's work, it's certainly one of the clearest examples of where possibly you might also get spin liquids. So I've never worked on them, so I've really not much to say. Dirk.
You sort of half suggested that your new result that you submitted to PRL defies the Maxwell equations. Is that so?
Actually, no, not that one. There's no, that's low-lying fruit. It's the other papers on anomalous dimensions for gauge fields that I was talking about. Not that paper. That's perfectly consistent with the existing Maxwell equations. Okay, yes. Okay.